Okay, welcome back to the structural reliability class. Structure reliability class. In the class, as I mentioned to you, I don't want to just talk in one way, so I really like to communicate throughout the classes, and I want you to talk. So otherwise, after maybe 20, 30 minutes, it's very sleepy. So, so I want you to talk, but I'll raise the questions to you also. Okay. So the title, last Friday I talked to you about the overall semester plan, what I want to pursue, what I want to do, things like that. On the reliability, but not the overall reliability, but I want to concentrate on the structure reliability. And Friday, I happened to talk to the Anjun Kwon. He took the reliability course in mechanical engineering department out there. And I discovered my content of the course is somewhat different from those classes. I don't claim the way I deliver the lectures, contents are superior, no. But I know the fact was lacking in the class, as I taught so many years. So this time I want to teach you the computation methodology in addition to the basic principles of structure reliability. Just knowing as a graduate course, just knowing the basic concept is not enough. If you want to implement the methodology into your thesis work, you have to know how to make a computation, to really looking into the structure, system safeties and all that. So that's what I'm going to teach you. Not only just the formulation, start from the general structure reliability formulation, then going into the detail by you conducting the project, then you will write the program yourself, of course, maybe two people together. Then you will present in front of the class and we'll discuss about it. So, which is, I feel, more meaningful. So for next 1 month, I'm going to really talk about probability related topics because first it's going up, you know, it's weird. Going up, I don't know why it's going up. structure or structure system. It's both, okay? We are dealing with the system. Here, if I just draw the big circle here and put the core, so this is a reliability here. Inside the core, okay? Surroundings, large core is probability. It's all probability based, not the deterministic. We are very familiar with the deterministic in the design concept. All the ship design is deterministic. And of course, the way they handle is they use a facility. They use a kind of the advanced technology like a CAD program, use IGES files to generate FEM models to make the life easier. When they pull out the drawing to generate the current design, that's 1945, the drawings. I don't know about the Korea, that's what happened in US, the naval ships. So then they deviate from there. But this is a really kind of a new concept. Many people struggled to really establish the criteria or baseline to conduct the reliability. Within the reliability, structural reliability is more another, maybe you can say, the core inside the core, okay? So understanding the probability is like understanding what's happening in the real world. It's not just to compute here is a loading which is a constant loading. Then I have a material which defines by somebody else saying that yield stress, ultimate stress and all that. Then I can compute the result, whatever the result is, okay? Then you will be happy. You are very happy because you are looking for one result. One result, not the two result or three result, which is called analysis. Which is called, for the analysis, you're always looking for one solution. Analysis, you always look for one solution, not the two solutions. That's analysis. But for the design, are you looking for one result? Yes or no? Say something. Yunseok, you're looking for one result? Design. For design, you are not looking for one result. And Yunseok's idea may be quite different from Higu's idea or Yonghyun's idea because your background, your personality is all different. For the design, some design for the car, you can design the Rolls-Royce, or Yonghyun can build a tank as a car, which he can drive a very expensive way of dealing, but design. So I said, okay, well, let's design the car, automobile. Then there will be all different kind of the design. So if you come up, I have this type of the design for the cars, so then my answer will be acceptable. Then Higyu has another. He loves Volkswagen, small, fast, can just go anywhere. I saw the magazine, that's what he bought it. I think it is all a compact car. That's his design, and that's what he likes it. Then if he designs such a small, compact, efficient car, that's acceptable. The Yonghyun is a naval officer. So he designed the tank as his personal car. Then what can I say? I will say it's acceptable. All different design kind of the idea is acceptable because it is design relevant. So analysis and design, remember, is totally different. Okay? So in this class, I'll try to attempt to bring out such ideas and concepts. Then I want to see your really your heart, what you have in your mind to bring up. That's what the design is. All the ocean plant has to be same. At the beginning, maybe similar each other, but eventually it would be all different. Cell phone, is it all same? Cell phone, there are all different kind of the cell phone. All the days, this kind of the cell phone used as a really phone, we feel is stupid. Because such a shape for the phone, we never accepted this kind of the phone. All different design. Advanced design, but design is a design. Whether it's advanced or primitive, it's all design. And Stephen Jobs, he really developed a mechanism to just using the fingers to change the page. Is that his own idea? Is it his own idea? I heard it's not. I'm not going to say much on that because it's recording. So somebody could sue me, so I don't want to tangle up in a soup. So it's a design, ideas, design. So you're so young, and that's what you should be looking for in the future. Reliability-based design comes after really analysis. But iterative process of analysis is not design. That's one kind of the procedure, but analysis and designs are totally different. Design coming from the scratch. Okay, it's just a creative arts. That's what the design is. So as you look at you in graduate schools, you spend lots of hours for study and research, but before you dive into spending hours and hours, think a little bit about where I'm heading for. You just spend the whole night and come home at 5 o'clock in the morning. Ask yourself, did I spend very effective hours this time or not? That's very important. So analysis and design, two different things. Within the analysis and design, probabilistic design. Within the probabilistic design, I'm talking about reliability-based design. Reliability, then you are dealing with the safety. Structure reliability, you are dealing with structure safety. Okay, so usual design concept within the structure analysis and design, I can say that one is, as I just mentioned, deterministic design. Another approach I'm dealing in this quarter is probabilistic design. Probabilistic, specialize within the probabilistic. I'm talking about reliability based design. Okay. The person he was here was chemical engineering background. All of you has experience to take the course about the strengths of material. Everybody has experience. The reason I'm asking is, doesn't matter whether you know or not. In ocean systems engineering, if I'm aware some of you never exposed to strengths of material, then I can really, whenever I teach, I can put the background, talk on the background. Everybody has a strengths of material, which is sophomore course, really. Everybody? Whatever the design in civil engineering, mechanical engineering, that type of area, you are dealing with load and strengths. So load in deterministic approach is a constant. Of course, I'm dealing with the static model. Dynamic model, of course, is a time domain parameters. But let's say load, constant. Okay. And the strengths, of course, a constant. That's a deterministic design. There's no statistical variation for strength and load, dealing with a constant. Constant. What about the reliability-based model? Reliability-based model is, the load is probabilistic distributions. It has not a constant, so probabilistic. I'll tell you what that means. And of course, for the strengths, could vary. Whether it's really dynamic or static, it has a probabilistic distributions. Okay. And for the deterministic design, then whatever the load, whatever the strengths, people worry about it. Is it gonna be really safe design? The question is it really safe? So if I design based on that particular constant load, is my structure system is it going to survive, not collapse? Structural safety is the issue. Then, as I mentioned last Friday, then you are dealing with safety factor. Or you may call that unofficially fuzzy factor, fuzziness, not clear. So why you use a safety factor? Simply speaking, for building design, floor loading, office floor loading, I use something like 100 pounds per square inch. But who knows, it could be 150 pounds per square inch, or could it be 200 pounds per square inch. So then you have to apply so-called uncertainty in the whole system. Uncertainty. So to cover uncertainty, you have to introduce the safety factor. Very usual approach. If you look at, when you build a ship, of course there is a ship manual. If you turn the page, then you should be able to discover what safety factor for that particular ship they propose. Of course, there is the basic guideline or code, pre-stressed concrete or concrete itself. There is a code recommending the safety factor. Nuclear power plant reactor has a safety factor which usually larger than 3, safety factor of 3. If safety factor is higher, that means its uncertainty level is higher. Then don't know much about it. Some 30-some years ago, I worked at Argonne National Lab in Chicago area, which is really nuclear lab. They designed a nuclear reactor. Then they really build a prototype and operate and all that. Then they don't know the reality, what's going to happen in case of accident. Then they, of course, expect to lose a coolant, like a Fukushima plant. Then what happened? Then transient loading comes up. For the boiling water reactor designed by GE, has a so-called chugging loading. In case of accident, of loss of coolant accident, then some steam column blowing down into the pool and sucking back that steam column back, so it has a chugging load. In the design, they never anticipate such a loading, never anticipated. Then in the testing, they found such a loadings. So they recalculate all the strengths and all that. Then they claim that our reactor is safe. How? Because they introduced a high safety factor to cover the uncertainty. So whenever you face the design, like our ocean systems engineering, the plant, ocean systems plant, then you have to really looking into why they really apply high safety factor to cover the uncertainty, okay? But reliability-based design introduces a probabilistic distribution of the load and the strengths. So it's all implemented, such a safety factor concept. They don't use it because it's already introduced the distribution, probabilistic distribution of a given important design parameters. It's all in there. So here, as a result, of course, then you compute the probability, okay, probability of failure. Rather than computing the whether as an end product, switching back here, as an end product, you want to make sure that the strengths, you have to make sure strength is higher than the load, assuming the unit cell same. You want to make sure that strength is higher than the load, so it's not going to collapse. That's a simple kind of the approach, but for the reliability design, you compute the probability of the failure, because any existing system, whether it's a mechanical system or structure system, you are dealing, what's the chance to fail? Anything can fail. Tacoma Bridge in Seattle area is a beautiful, beautiful arch type of the bridge, well designed in late 1930s, and but it collapsed. Anybody heard about that? Tacoma Bridge, Seattle and Tacoma is just in the south, a little bit connecting to the cities. That's really arch bridge, but by the self-excitation due to the wind, once it swings, then it's the self-generating mechanism of the wind loading. Then it's just it's like a fluid elastic phenomena. It's swing more and more, eventually collapsed. So probability of the failure is what the reliability-based design or analysis looking for. Then you have to, of course, set up the design probability of the failure. Probability of the failure is equal to 1 minus probability of the survivor. Probability of the failure plus the probability of the survivor is equal to 1. That's basic, right? It's a complement each other. So probability of the failure, PS, is a probability of survivor. So if you compute the probability of the failure, then you know the probability of the survivor. Okay. Probability of the failure. For the design concept, for the design, you want to, before you start the design, you want to know the level, or you want to define the level of probability of survivor. Then you can design. You follow me? For the analysis, is slightly opposite. For the analysis, you will end up computing the probability of the survivor or the probability of the failure, because all the given system is provided. For the analysis, you don't have to use your beautiful creativity. Everything is provided, then you compute whether the structure system is going to be survive. What's the chance to survive? Okay, that's just analysis. But for the design is, you have to build a system which it has given the probability of the failure, or given the probability of the survivor. It's already predefined based on the whatever information's available. It's two different things, remember. Okay? So this is kind of the end product, and this probability of the failure and safety factor in the deterministic approach has a relation. This has a relation. That relation is not the two separate things. It is connected. How it is connected is what I'm going to show you as a part of the course. And that's what I recommend. The second book, I think you don't need to buy, just to check out from Higyu, then use it, then return. I just have a 2 set. I don't think we need more, but if you need more, I'll get some more book. So that book, written by Elishikov, good friend of mine, I want to invite him sometime in KAIST. Sunday he doesn't work, regardless. Why? You work sometimes. I insisting my students in the lab, Sunday, don't work. Just to rest and look at some other nice fictions and novels and whatever. Relax. 1 out of 7 days is a good idea that my brain can rest. He never works on Sunday, regardless. Doesn't matter how busy it is. Why? He's Jewish. in Jewish, of course, they have their religion, trusting the God. But Bible said in the Old Testament, 1 day you rest. That's what they do. It's a beautiful scheme. We talk quite a bit on that. So that's book. Second book in the list there is safety versus reliability. How does it relating? How we can communicate that together? Can I use somehow the safety factor based on the reliability analysis? My answer is yes. His answer is, of course, yes. Is it friend or enemy? My answer is a friend, a very good friend. It's not the two separate entity. Okay? So this is what then you can go further. So depend on the analysis or design, you can define all that. In the reliability-based computation, we're going to develop so-called safe region and failure region. You will find this is safe region. This is a failure region. This is not a line. This is a failure surface, so-called. This is a failure surface. If your design falls here in this region, it's of course you can visualize 2D. Okay, 2D is formed by two random variables, something like a load and the strength. Okay, but if it's a three-dimensional, you can still see three different parameters, probabilistic parameter like load, strength, or like Young's modulus. Could be variable. When I say variable, here it's really random variable. It can vary. Then depend on where your design location is, then you can have a safe design, then you can have a failure kind of the design. It will fail. You can compute that. But a given reasonable parameter. That's what I'm going to show you for mathematical formulation. I'm going to give you the file, then you can copy it, or you can just use electronic file, which I got from Professor Du in University of Missouri, Rolla, Missouri. That's the easiest write up to understand the methodology. Mr. An told me he took the course on reliability, but I don't know how to compute the result. But he understands all the basics. What's the reliability? What's the probability model to do the reliability? He knows normal distributions or Gaussian distributions or log normal distribution, extremal distributions, Weibull distribution, all different model. Then if you can use it, what's good for it? So that's what I'm going to cover. So that's the region stuff. Okay, how to introduce the probability concept in reliability analysis and design. Of course, most of you know because you took the statistics course, but some of you may not take the course yet. How many didn't take the course yet? Probability course, raise your hand. Would you willing to take the course at least the next semester? Because you guys are doing doctoral degree, yes? Yes? Okay. I demand. Why? to understand what's happening in real world. Everything is a probabilistic. There is no such a thing as a fixed success. But as I see the namchin yachin, there is no 100% probability of success. There is always a probability of the failure before they marry. Everything in the world is probabilistic. Say yes. Yes, it is probabilistic. So, for example, to conduct a reliability-based design and analysis work, I have to know the probabilistic distribution, for example, of load and resistance. If you don't know, it's very simple. If it's a simple, this is a bar, maybe steel bar, then you can have loading P. P is not the good way. I'm using it as a probability. So force, like a sinusoidal force, or simple tension loading, given tensile loading. And you go POSCO in Pohang, then get 100 specimen from the steel mill, for example, little specimen, 100 specimen. Maybe 1,000 specimen is better than 100 specimen to test out, then get the good distribution, probabilistic distribution of like yield stress. You know all the yield stress. So then you will say, Professor Chen, you are insulting us. That comes from sophomore textbooks. You all know that. Of course you all know that. I usually, when I revisit, talking the same thing twice or 3 times, then you know what's going on. So 100 specimen, then test. Then you can list out the table saying that the number of specimen. And here is yield stress. Yield stress, if I simply draw, this is epsilon and sigma. Then you have a pull testing. If you pull it for steel, not aluminum, steel goes up, right? It goes up for the steel, then neck down, then here, then breaks off. Typical steel, any specimen, of course, this is a yield stress. Okay, neck goes up before neck down. That's yield stress. That's what typical for machinery design, machine design, or mechanical element design. That's what the limit you are using it, because up to from here to here is linear relation between the sigma and the epsilon. Stress-strain relation is linear. After that is nonlinear. And this is just a fracture. So this is what the usual measure, important measure of the stress is. Then each specimen, 100 specimen, you do the pulling test. Then surprisingly, you could say, oh, okay, about 30 out of 100 specimen has 36. I'm sorry, I'm using the English gravitational unit, but you can use metric systems, and 1 megapascal is about 145 psi. KPK is 1,000. Then some are something like 5 has about 50 kpsi. Some 10 are something like 40 kpsi. Some are like 5 kpsi. Few specimen is that range. Is it realistic? It is realistic. It comes from the same batch, but it has a different strength. It's realistic. Then you can plot this. Then you can, of course, make it 10, 15, 20, all that, right? Then you can build like this. This is yield stress. And this is a number of a specimen which related to sigma y, yield stress. Then you can put, oh, okay, so this is a 5. You can draw the point. You can draw it. This is a 10. You can draw another point. Then eventually 36 kpsi is 30 here. This is number of specimen. Then you can connect it. Of course, if it's 0, nothing. So it's going to go something like this. As this number goes higher, then less number of a specimen. What do you call this? This is a probability density function. You heard about it, don't you? That's what the probability density function. You have to massage it through the probability density function, then connect it to a particular model, particular probability model. So Friday or Monday, I'm going to assign the first very nice project, straight project. Then you can start to think. I want to really develop the project with your help, some meaningful project. Then you can really use your ideas, use your wonderful brain. You have a beautiful, wonderful brain. That's what I want you to put it out in this course, and you develop yourself with my help. I think that's the way we should go in this course, okay? Okay, now is 5 more minutes and I'll quit. So now this, I just roughly draw this. Then you will end up getting that, such a point to connect. Then really conduct something like a regression analysis and all kind. Then have a beautiful curve fit into the probability model. One of the first well-known probability model, I'm going to say that this is generally fx. This is a capital letter. F is probability density function. So this is, F is, I'm always using as probability density function. F. So here F is a probability density function. Probability density function, I'm gonna just name it as a PDF. Probability density function. You know. But when you didn't take the course, that's fine. What you have to do nowadays, you are really living in the beautiful world. Too much information. In my era, I don't have too much information. Like internet, we didn't have the internet in 1960, 1970, but we had a beautiful time. You have too much information, but that's great, isn't it? Then go internet, just punch probability density function. It spells out so much information, it's a headache. But do that. So everything is all there. Even classified information I found is in there. So F, and the subscript, the alphabet, let's say X. This X is a random variable. When I use a capital X, that's a random variable parameters, okay? Capital X, if you see in this class, I could make mistake, but that's a random variable. So here, what's the random variable? Yield stress. It varies. It's a random variable. And then I use a small x. When small x is particular outcome, is kind of the probability way of saying it. It's a particular outcome. So X could be here, particular outcome, particular outcome, particular value in the random variable, particular, okay, given, assigned. So this is what the probability, the density function. If you, so I'm going to just draw over here. It's like upside down bell shape. If it's not, I think this is upside down bell shape. This is one of the most popular, the probability density function. What do you call? Gaussian distribution. But if you didn't take this, fine, just accept. You know, when you are young, easiest thing is you just open your heart. That's the beauty. You just accept it. You know, that's all it takes. But when you become over 30, then you don't accept easily. You toast the fact up there, looking this way, looking this way, then accept it. Bad. The school I used to teach in U.S. was Naval Postgraduate School. The students are all like lieutenant mostly, major, and age is about 30, 32, 33. They don't accept the fact easily. But for 20s, regardless of what I say, they accept it. Sometimes accept the wrong things, but accept it. If I make mistake, I'm telling you, I made a mistake. We have to be honest to each other. No, that's the best way. Teacher, students, you could make mistake. I could make mistakes, right? So it's a normal probability density function, or the Gaussian name of the person. Gaussian probability density function is a symmetry about the center. So this could be x, and this could be fx. Typical model, lots of physical phenomena fits in this model, like a yield stress. This is a perfect model for Gaussian. Okay, we'll stop here. Then continue on Wednesday. If you feel it's boring, tell me it's boring. I'll bring some drink, then you can enjoy. Okay, so I'll see you Wednesday.